Lesson 9.3, testing two variances. I know it seems strange that we would go this quickly into variances. Usually this is the last lesson of the chapter, but this is actually something that we will need to proceed forth with the next few lessons. So here we go. So testing two variances. We're going to start with what does this mean, and these tests are actually fairly easy compared to some of the ones we've done before. So what you need to do, you need to realize, first of all, the value of f cannot be negative because variances are always positive or 0. The distribution is positively skewed, that's not that important. The mean value of f is approximately equal to 1, and the f distribution is a family of curves based on degrees of freedom of variances of the numerator and the denominator. Okay. So a couple of things. So this is the test you're going to run. It looks really basic, okay? This is nice. So the f-test is going to be the standard deviation of one sample squared over the standard deviation of another sample squared. Now, it doesn't matter which one you have first listed in your in the things that you have. The larger of the two variances is always placed on top because that's how we're going to get our f value. Now, the f value is going to be compared to another chart that I will show you in class tomorrow how to use. It's a little complex, it's different than the ones we have used. So I'll show you some things in the examples today, but we'll have to talk more about them in class tomorrow. All right? So there's degrees of freedom for the numerator and for the denominator. So on this chart, you actually have two different lists that you're looking at. So the sample size for the larger variance is always n1. It's always the one on the top. So let's look at an example. Now, this is a really bad example because it was supposed to be just looking in the chart, and I forgot to put the chart on there. So we have these samples, and you're basically looking it up in the chart. What's the f value in the chart? This is not running a test at all. So the sample 1 variance is 128, and the n value is 23. The sample 2 variance is 162, and the n value is 16. There's a chart where you look across the top and across the side to find these values. It's two-tailed at alpha equals 0.01, and we simply look up that value in the chart, and we find the f value. So now I wrote down the degrees of freedom and that kind of stuff so that you understood. So the degrees of freedom of the numerator is going to be 15 because that standard deviation is bigger than this one. Okay, the degrees of freedom for the denominator is going to be 22 because that one is smaller. So when you write it up, this would be on top of that one. Okay, the critical value, if you look in the chart, is 3.36. But we'll look at the chart tomorrow. Now, practice 1 is really nice because it actually gives you the chart. So go ahead and write down what you need from this, and then let's look at the solution. Okay, so here's the solution. So it's a right-tailed test with alpha equals 0.05. So there's more than one table. So this is the thing with this. There's multiple tables for these. So there's a 0.05 table. The degrees of freedom of the numerator is going to go along the top, and the degrees of freedom of the denominator is going to go along the bottom. And then you simply look for the number that they match up together. In this case, 2.18. Okay, so how do we do this? We're going to use this test, and we're going to see if the f value that we get when we calculate is going to be greater than the f value from the chart. So here's just a couple of notes. First of all, this is the formula. The larger variance is always placed in the numerator. It's a two-tailed test. The alpha must be divided by 2. And in the standard deviations are used instead of variances. You must square them. If the degrees of freedom cannot be found, the closest value on the smaller side should be used. So here's our example 2. It says a researcher claims the standard deviation of an age of cats is smaller than the standard deviation of the age of dogs who are owned by families in a large city. A randomly selected sample of 29 cats has a standard deviation of 2.7 years. A random sample of 16 dogs has a standard deviation of 3.5 years. Is the researcher correct? Use alpha equals 0.05. So let's look at in this example. First of all, we need to set up our hypotheses. Always the first step. So we're going to set up a hypothesis. H naught is that the standard deviation of the first sample is going to be greater than or equal to the standard deviation of the second one. H1 is that the standard deviation The first one is going to be less than the standard deviation of the second sample. Okay. So, because we think the cats are going to be smaller. Critical value is 2.04 at alpha equals 0.05. We looked this up in the chart. Degrees of freedom of the numerator is 15. Degrees of freedom of the denominator is 28. So we put the bigger one on the top, which is going to be the dogs. So 3.5 squared over 2.7 squared gives us 1.68. We do not reject, so we can't say that there's any significant difference in between the standard deviations. All right, so here's your practice problem. Go ahead and try it by plugging the numbers into the formula. Obviously, you can't look up the chart, but you can do the rest of it. And here is your solution. Anybody know? There's your solution. Okay. Let me play it just a little bit because I'm going to move this thing. I think. I hope. No, I didn't. Okay. Okay. So the hypothesis is that they're equal and not equal to. Okay, we use the chart with the degrees of freedom of 25 and 17. We compare the critical values, and we get and we compute the test value, which is 3.6. It's bigger than 2.56, so we can reject.